Hello, welcome to es346 Basic Thermodynamics. These are examples, and what we're going to discuss today is when to use heat capacity. I'm Rourke Peterson. So here's the example problem we're going to do. We have a constant pressure piston cylinder device. It contains 1.5 pounds of water vapor at 40 psia and 280 degrees Fahrenheit. 50 BTUs of heat is added to the system, and what we're asked to find is what is the temperature of the water. So over here we have a diagram, and we have 50 BTUs that are going into the system. And we are told some initial conditions. We're told an initial temperature and pressure. So I have a temperature and a pressure. I'm also told that it's water vapor. So I'm actually already told what the state is. But we could go ahead and confirm that we actually have a vapor by using the property table. So let's go ahead and do that as a little bit of review. I'm going to go over to the property tables, and we were given a pressure, and our pressure was 40 psia, and if I look across, I realize that Tsat, the temperature at which water will boil if it's at 40 psia, is 267.22. So I'm going to go back to my problem, and I realize that Tsat is equal to 267.22 degrees Fahrenheit. And that is less than my temperature of 280, which is what I'm at. So I am superheated. I'm above the boiling temperature. So it sort of confirms that I have a water vapor, and in fact I have a superheated vapor. So now let's go ahead and look at our system over here, and we're trying to find out what that final temperature of the water is. So we're going through a process. So we're going to go ahead and apply a first law energy balance that says the change in energy of my system is going to be the energy that goes in minus the energy that goes out. And so looking over here, I have a closed system, so the change in my energy is going to be the mass times the change in internal energy. I'll write that m times U2 minus U1. And then what energy is going in? I have this heat being added, so I'll call that Q going in. And as this is heated, this is a constant pressure piston cylinder. Therefore, that piston can move upwards, and so there's going to be some boundary work, and it is leaving the system because the system is doing work on the atmosphere and expanding. So there's my energy balance, and it's a constant pressure. So I can actually very quickly find out what that boundary work is, and that's going to be equal to that constant pressure V2 minus V1, where those are extensive volumes. And one of the nice things I realize is that, I'm going to go ahead and rewrite my left-hand side here, is that I can go ahead and combine the PV with the U term, and I have M, and this I can write in terms of enthalpy. M H2 minus H1 is equal to Q, just kind of a couple less terms, and we've looked at that in a previous video. So now here's my energy balance, and I'm given what Q is. It's equal to 50 BTUs. And so the final state is going to be determined by this value of H2, and my pressure is constant, so it's going to remain at 40 psia. So I'm going to end up with, instead of knowing a T and a P, I'm going to end up knowing an H and a P, two independent intensive variables. But I need to find out what that H is, and that H is going to be H2 from the energy balance. So how do I determine what H1 is? So to do that, I need to determine now whether this is acting as an ideal gas, and I can use a heat capacity, or if I should be looking up on a table. So let's go ahead and do that. And what I want to know is how well this behaves as an ideal gas. I can kind of quantify that with that compressibility, and if that compressibility factor Z is near 1, it's an ideal gas. In order to determine my value of Z, let's look at what our reduced pressure is. Remember, reduced pressure is just the pressure normalized by the critical pressure. So I'm a pressure of 40 psia, and now I want to find out what the critical pressure of water is. So let's go to our property tables, and I need to define my critical properties. That's in A1. So I'll go up here to table A1. I'm in English units, A1E, and I'm looking at water. So water's down here at the bottom, and there's my critical pressure. If I look down, is 3200, and the units are psia. So 3200 psia. Let's put that in there. And so I have 40 over 3200. That's a pretty small number. That's 0.0125. So there's my reduced pressure. Now, normally I would go ahead and find my reduced temperature as well, so I could find my value of Z. But actually, that number is so small. Let's go back to our property tables. Let's go look at the compressibility charts. Here we go. Here's the compressibility chart, and I'll go ahead and blow that up a little. Unfortunately, it's a little hard to read on the screen here with the green. You can confirm this when you look. I'm at a reduced pressure, 0.0125. I'm way over on the left. No matter what the temperature is, all my lines are right around Z is equal to 1. So I don't even need to bother calculating T. I know that Z is essentially equal to 1, which means it's an ideal gas. So now I can go ahead and take this equation and I can replace H with the heat capacity, and it's going to be mCp T2 minus T1, and that's going to be equal to Q, or 50 BTUs. And so now I'm going to be able to solve this equation directly for T2. So let's put our numbers in. 1.5 pound mass. Now I need the heat capacity. It's like heat capacity of water. We need to go back to our property tables here. And let's go down. So back to our English tables. And A2, these are ideal gas specific heat capacities. And water's acting as an ideal gas. So let's look through. And we don't see water. What we see is steam. And that's because in order for water to be an ideal gas, it's got to be in the vapor state. We normally call that steam. So there's steam, my bottom column. There's a symbol H2O to confirm it. And I'm looking for Cp because I'm doing enthalpy, and it's 0.445. So let's go back here. Cp is 0.445, and the units on that are BTUs per pound mass Rankine, and I have T2 minus the initial temperature, which was 280. That right there is equal to 50 BTUs. So now I'm just going to solve that equation for T2, and if you do that, T2, we should realize, is going to be about 355 degrees Fahrenheit. So there's what my final temperature is. 355. Now notice this is degrees Rankine, and I did this in degrees Fahrenheit, but that's okay because this is a per degree Rankine, just the size of a degrees Rankine, and the size of a degree Rankine is the same as the size of a degree Fahrenheit. It's just their absolute value, so it's fine to leave that in terms of degrees Fahrenheit. I also could have added, if I wanted to, just added 273 and added 273 to both those values, and I would have found out those two things would have canceled because of this minus sign, and I'd end up with the same value. So there's my final value, 355 degrees Fahrenheit. Oops, let me go back to our problem here. And let's look at this. What I'm going to do now is let's just flip it. And the only thing I'm changing is saying let's start with the same conditions, but what if 50 BTUs is now removed from the system? So instead of it being added, it's going to be removed. So my energy balance, I realize now, it's going to be M U2 minus U1 is equal to Q. And at this point, I'm going to be adding plus WB because at this point, work is going to be done on the system. And this is going to actually be a minus Q because heat's going to be leaving the system. So this whole thing is just going to end up being flipped in terms of the direction. So if you recall before, we had a delta T of about 75 degrees Fahrenheit, and at this point the temperature is just going to be dropping instead of it going increasing, which would make sense. We just switch the direction of all of this. So therefore T2 is equal to 280 minus 75, and that would be a temperature of 205 degrees Fahrenheit. Right? Now we got to be careful here though, because I went pretty quick on that, and there's some assumptions we made in order to end up using this equation where we had M H2 minus H1, and then we made it into M Cp T2 minus T1, was that it was an ideal gas. And the question is, well, does it still behave as an ideal gas if I remove 50 BTUs of energy? Well, this predicted that I'm at 205. Now remember, we saw what Tsat was at this pressure, constant pressure of 40 psia, and Tsat was 267.22 degrees Fahrenheit, and that's greater than 205. So I'm now below the boiling point, which means that I'm condensing, which means there's no way I'm acting as an ideal gas if I've got some liquid in here. So actually, I can't go ahead and do all of this that I did right there. That's wrong. We're going to have to do it differently. So let's think about what's going on here. Let's draw this as a TV diagram. And initially we had a superheated vapor out there. we're removing heat at this point. We're doing it at constant pressure. I'm going to follow an isobar. At some point, I'm going to hit the saturation curve, and I'm going to start moving straight across. And in fact, if I keep removing heat, I'll end up becoming a saturated liquid, and then eventually the temperature would drop. So what I want to do now, if I want to figure out my temperature, is I realize I can't use ideal gas law. I'm going to start going back and looking at my tables here. So, all right, so I'm going to go back here. Let's go back to our energy balance. We have M H2 minus H1 is going to be equal to minus Q. All right, so I've got, this is now just a heat that's leaving the system. And I now need to determine, I'm trying to figure out what my value of H2 is, and I'm going to do that using the tables. So what I'm going to do is put my 1.5 pound mass there, and I have H2 minus, and I need to find H1, and so H1 is going to be at these conditions here of 40 psia and 280. But now I've got to go and use the tables for this. So what I'm going to want to do now is go to my superheated tables, move on down here, superheated, and we're looking at 40 psia. So that's this table right here. I've got 40 psia and I'm at 280, and so my value of enthalpy, that's this column here, my value of enthalpy is 1176.6. So let's put that in there, 1176.6 BTUs per pound mass, and that right there is equal to minus Q, or equal to a minus 50 BTUs. And now I can go ahead and solve for H2 from here, and H2 is going to be equal to 1143 BTUs per pound mass. And so now I know what this value is. If I wanted to figure out what my state is, so I can determine what my temperature is, because actually if I'm a mixture, I'll be able to get my temperature pretty easy. I need to compare that with, well, the value of Hg, of course, the value of H corresponding to that point there. So I'm going to go back to our tables and let's look at saturation. In fact, actually, I can get it right here. So here, my 40 psia. The values at saturation, H is 1169 right there. It looks like 1169.9. Oh, that's the vapor. I want to compare this to liquid. Excuse me. So we need to. I'm sorry. That would be the value of a saturated vapor. I want to compare it to a saturated liquid. So we do have to go to the saturation tables. So here we are in terms of pressure. We're at 40 psia. I look across. I'm comparing this to HF, which is 236.14. So, all right. So this right there, HF is equal to 236.14, and I realize that my value of H2 is greater than that. So therefore, I'm at this point, and my temperature is simply the saturation temperature, which we found at the very beginning of the problem, and that was 267.22 degrees Fahrenheit. So kind of a lot of math in here just to kind of end up getting a value I read off the table, but it's because I had to determine what my final state was, and I had to use the tables to do that. So we can do one last thing just to wrap this up, is now since we have a mixture, let's go ahead and determine what is the quality. And so remember, I just calculated my value of H2 at 1143 units of BTUs per pound mass. If I sketch up a TV diagram again to remind myself, I started at some point out here, followed an isobar, and then ended up with a mixture at some point to there. And so I'm going to go ahead and take an average between that value of Hg and that value of Hf right there to go ahead and calculate my value of X2. So X2 is going to be H, or H2 that I have, minus Hf over Hfg. That's just the difference between those two values. And I'm going to go to the tables to get that. So again, I'm at 40 psia. I just saw Hf at 236. My Hfg value right there is 933.69. So let's go ahead and put 1143 minus, we just said 236.14, and then Hfg was 933.69, and that's going to go ahead and give me my value of X2 at 0.97. So nearly a vapor. I'm actually probably a little closer to the right-hand side there, but I have a mixture, and so there's my quality of X2. And I could then use that to find other properties, like, for example, if I wanted to know V2, that would be equal to VF plus X VFG. I could go ahead and find U2 with a similar form, and eventually we'll see we can find values like our entropy doing the same thing. So, all right, well, that kind of wraps up our example of when we can assume ideal gate behavior and use heat capacities, and when we need to go ahead and use the tables.